Okay, great. So I'll give you guys a minute to read that XKCD comic. Thank you very, very much for being here. It is a great honor. I've heard so much about Larry Brown from many, many people, my advisors included. And it's a real honor to have won the award. So it's kind of an accident, really, that I'm giving this talk along with Kerry Mengerson's talk just before. But I do want to say that, at least spiritually, both of these themes are quite related. What I'll be telling you about today is about a class of flexible non-parametric models for learning from data that humans generate. And crowdsourcing is actually going to form a large motivating application. Unlike the other talk, though, this is going to be much more mathematical statistics oriented. And I'm going to focus on some fundamental questions at the intersection of statistics and computation. Hopefully you'll take away that one line from this talk. And I'll try and keep this relatively high level and tell you about the landscape of problems that I find interesting here. So like Jiong said, so this talk is going to be about 50 minutes. And if you have questions in between that you feel you need to ask, then please just chime in. I don't mind stopping and answering those. It's not absolutely important that I get through everything as long as you get something out of it. Okay, great. So let's just start off with these large motivating applications. In particular, humans generate data in a variety of settings. For instance, by expressing choices over assortments in marketplaces. They also generate data by they also generate data by answering test questions in many evaluation tasks, tests that are becoming increasingly difficult to administer now with the pandemic and so on. Crowdsourcing is going to form a large motivating example, like I said, where you can use the crowd of non-expert humans in order to inform various downstream tasks. For instance, this example here is a 2D image where the crowd has been asked questions about the depth in that image. And these data that the crowd will generate will then be used downstream to create a depth map from that image. There are other examples, and Kerry Mengerson covered some very, very cool ones in her talk. There are also examples in diagnostics. I believe Susan Holmes mentioned one of these, where you can use the non-expert crowd to annotate data that can then be culled down and then seen by experts, for instance, in diagnostic applications like these. Right, so human data like this is prevalent all over the place. You can collect it, for instance, on crowdsourcing platforms. It's cheap. So what you'd really like are models for such data that are interpretable as well as flexible. And this talk is going to focus on such a flexible class of non-parametric models for human-generated data. And we're going to focus on foundational questions that surround the fitting of those models. So what's a prototypical example of data that humans generate in this fashion? It's choice data. And in particular, the simplest form of choice is given by a pairwise comparison, a choice between two alternatives. So this is a scalable way to collect human data. Ask them to compare two alternatives. Now, clearly there's a correct answer to this question, but the crowd is going to give you noisy feedback because they're going to be subjective in their own possible ways. What's a good way to model this noise? Well, as a probability. That's a stochastic model for such a choice between two alternatives. What's the probability that one is chosen over the other? Now, your data set is not going to have just two images. It's going to have many. And this defines a comparison probability matrix indexed by items on either of the dimensions. So these items are boxes for the simple reason that I couldn't think of anything else, but they could actually represent a variety of things. For instance, in massive online classrooms, these items are tests of students. And pairwise comparisons are known to be a scalable way to perform peer grading. In crowdsourcing examples, like the one I just flashed on the screen, you can also use pairwise comparisons for various downstream tasks. For instance, to narrow down your search to smaller portions of the data set. Now, it's important to understand that the data itself are not these probabilities, they're wins and losses, the results of pairwise comparisons. The model here is that these zeros and ones are actually drawn as random variables from the underlying probabilities. These are Bernoulli. So this is a probability model for your data. What's a statistical model? Well, it corresponds to a collection of such probability models. In other words, structure on that underlying comparison matrix. Now, on the one hand, you could choose to be completely flexible. Besides positing the natural symmetry relation that the probability with which I beats J is 1 minus the probability with which J beats I, there's no further structure on that matrix. Popular models are very structured on the other hand. They are parameter based or weight based. Each item is associated with a scalar weight, item I with weight Wi, and the probability with which I beats J is given by some function of the difference of these weights. Now this function is typically known, it's monotone, and depending on how you choose it, you get a variety of popular models. For instance, the logistic function corresponds to what's called the Bradley-Terry-Luce model, and the Gaussian CDF gives you what's called the Thurstone model. For those of you who play chess, the Thurstone model is precisely what generates the ELO ratings as the various weights. Now, why is this extremely structured? Because we've taken the problem of modeling those n squared or n choose 2 numbers in that matrix and reduced it to just understanding n numbers, W1 through Wn. Now, the focus of this talk is on the interface. In particular, one member of that interface called strong stochastic transitivity, which goes all the way back to the 50s in sociology and economics, which says, let's get rid of these parameter-based assumptions on the left and replace them with just ordering assumptions. So notice that the parametric assumption on the left already posits an ordering. Large weights are better items. SST posits that we'll keep this ordering, but get rid of the parameters themselves. In particular, if I, J, and K are 3 items in the underlying ordering such that I beats J and J beats K, then there's a natural transitivity relationship posited by SST. The probability with which I beats K, that's further along the ordering, is greater than both the probability that I beats J and the probability that J beats K. Now, this is true for every such triple. That's what's posited by the model. And if you'd like to see this in a picture, simply look at that underlying matrix, put the best item on top, the worst item on the bottom. Then SST will say that the entries of that matrix will increase along each row. The probability with which I beat worse and worse items gets larger and larger. And by symmetry, there will be a decrease along the columns. However, I don't know which item to put on top and which to put on the bottom. And so there are 2 unknown permutations that define the underlying latent model. And for that reason, I will call this the permutation-based model. And this will form the focus, this and its relatives will form the focus of the rest of the talk. Now, there are many questions you could ask in such a setting from your data. For instance, give me a ranking from the data that I see. Give me a notion of quality of the various items. In particular, that second consideration actually corresponds to understanding the entries of the comparison probability matrix. Now, this was just pairwise comparisons, and it will form the focus of the talk. But let me give you yet another example, which is actually very related to something Kerry talked about earlier today, in psychometric analysis. So here, instead of modeling the probability with which items beat each other in comparisons, you're interested in the probability with which students answer test questions correctly. So that defines a matrix just like before, and you can start to put modeling assumptions on that matrix, right from the most flexible to the most structured. The most structured ones here again are weight-based. They associate with each student a scalar, each question a scalar, and posit that the probability is given by some function of the difference of these scalars. The Rasch model, which is extremely popular in this literature, is very, very similar to the BTL model in the previous slide. Again, in this setting, there is a permutation-based model. It goes back to Mokin in the 70s, which replaces the weights on students and questions with orderings over students and questions and an underlying isotonic matrix along both dimensions. Notice now that the permutations don't have to be the same. The student ordering a priori has nothing to do with the question ordering. And once again, there are lots of downstream inference tasks in this setting. You might want notions of student ability, notions of question difficulty. You might want to cluster students based on the questions that they answer, cluster questions, and so on and so forth. And all of these tasks correspond to understanding the entries of that matrix. Now, Kerry's example from the previous talk talked about crowd labeling, which is essentially the same setting where instead of students and questions, you now have crowd workers and questions. There are also examples in graphon estimation, for instance, where the similar type of flexibility in modeling manifests. The focus of this talk is for you to understand that this simple Venn diagram, that the parameter-based model is a strict subset of that permutation-based model in all of these cases. And this flexibility is known to give you quite a bit of gains in modeling real data. For instance, sociologists have noticed this for quite a few decades now when it comes to comparison data. And in modern crowdsourcing data sets, it is known that performing downstream tasks with flexible non-parametric assumptions under the permutation-based model can often lead to much, much lower error rates than using the much more restrictive parameter-based model. Now, I'm not going to dive into the empirics today because I have quite a bit of ground to cover otherwise, just in mathematical statistics land. But what I would like you to take away is that this class of models, the permutation-based models, are both interesting and important to study. And that's what we're going to do on the rest of this talk. I'm going to make things quite concrete. In the first portion of the talk, I will study the comparison setting, in particular pairwise comparisons. And in the second portion of the talk, I'll tell you about a natural generalization where you no longer have comparisons over two alternatives, but perhaps more than two alternatives. And throughout the talk, I'll try and discuss this interface between statistics and computation. It will manifest in the first portion of the talk when we look at worst case risk properties of estimation over this class. And in the second portion of the talk, it will manifest when we look at adaptation properties of various estimators. Okay, so without further ado, let me just jump right into the first portion of the talk on pairwise comparisons and the strong stochastic transitivity model. And this is joint work with Cheng Mao, who's at Georgia Tech, and Martin Wainwright, who was my advisor. But so weird to say it in the past tense suddenly, but yes. So pairwise comparisons are extremely classical. They've been studied for a very, very long time. They go all the way back to the 20s in the sociology and economics literatures. The strong stochastic transitivity model came sometime in the 50s, and these are two papers where some of the first mentions of it are. I love reading papers from the 50s in economics because they like saying things like this, which I really wish I could say in my papers. The more modern perspective in fitting these models from data has come from computer science, from statistics, operations research, probability. And again, this is just a sprinkling of the literature just to convince you that this is in fact a very large and vast area. And I will be adding just a little bit to this over the course of today's talk. Okay, so what's the particular problem we're going to focus on today? Like I said in my abstract, we're going to focus on model fitting. But before I do that, let me just give you, just fix some notation for the rest of the talk. We're going to consider two classes of models, the parameter-based model, para, and the permutation-based model, which I'll call perm. The underlying matrix now is going to be represented by M star. Throughout, I'll consider n by n matrices. So n is the number of items in the problem. And the permutation-based model, I'm going to allow for permutations that are different across the rows and the columns. This is just going to make thinking about the problem easier. Okay, so there's an underlying latent bi-isotonic matrix with unknown permutations. The observation model for today is going to be the most natural one. Take two random items and compare them. Do this again and again. So to make this a little bit more precise, think of a mask matrix Xi that's chosen uniformly at random from all matrices that have 1, 1 in some random entry. This defines the entry of M star from which you observe a comparison. And then Yi defines the result of that comparison. So notice that there are two sources of randomness, which entry you choose, and the Bernoulli randomness that comes from actually observing a comparison at that point. Okay, so we do this again and again, like I said, collect capital N samples with replacement, where capital N is somewhere between little n and little n squared. So if this hurts your head to think about, just think of capital N as being little n squared, in which case, roughly speaking, you see one sample of the entire matrix. Okay, but the other regimes of sample size are useful in thinking about sort of underdetermined settings, which are very common actually. Okay, so that's our observation model. What do I want to do at the end of this? The task that I'll consider for the purposes of this talk is going to be model fitting. Produce for me an estimate of the model, in particular the matrix M hat, and I will evaluate this matrix by measuring the squared Frobenius norm. I'll normalize that by the number of entries in the matrix. So this is an entry-wise error quantity, and that's going to define the risk that I'll consider for the rest of this talk. Now there are other metrics, and I'll cover a couple over the course of this talk, but if you have questions about the others, feel free to ask me. later. So this is a risk, but it depends on the unknown m star. In order to understand the difficulty of estimation in this problem, it's useful to have some notion of worst case risk. And that I'll call RC of m hat, where C is now a matrix class. So C is either going to be para or perm. And what we want to understand is the worst case risk of an estimator over either of those classes. The particular question we'll ask in the first portion of the talk is, are there tractable estimators, things that you can compute in polynomial time, say, with a small worst case risk? Now, this model fitting problem is useful to study even for pairwise comparisons, but it goes by other names. For instance, it's called calibration in crowd labeling or prediction in graph-on estimation. Okay, so I hope this setup is clear for the first portion of the talk. We're going to study this object, the worst case risk, and we're going to ask for computational tractability. What makes the question difficult is precisely that the fitting problem is terribly non-convex because of the underlying permutations. So let me now describe prior work on this problem. And in order to do that, I'm going to use this convenient two-dimensional plot. On the x-axis is going to be the worst case risk of an estimator m hat over the permutation-based class. And on the y-axis is going to be some proxy for running time. So in particular, that gray region is going to denote inefficient estimators, things that you can't compute, say, in polynomial time. So we want to be on the bottom left of this plot. So before we even ask for tractability, let's ask for the information theoretic limit of the problem. So there is noise. What's the smallest risk that can be attained, even if I gave you infinite computational resources? And that turns out to be lower bounded by a quantity that actually has a very natural interpretation. In order to interpret it, simply note that the permutation-based class contains the parameter-based class. And the parameter-based class has little n free parameters, W1 through Wn, and you see capital N samples. So that's the parametric rate. And that's a natural lower bound for this problem. What's surprising, perhaps, is you can prove an analogous upper bound of the same order up to a logarithmic factor. And now let me interpret this for you. Notice that the permutation-based class is strictly larger than the parameter-based class. That's what reduces the bias and gives you flexibility. But what this result is saying is that, at least in this worst case sense, the variance is comparable. In other words, the number of samples you would need to fit a permutation-based model is comparable to the number of samples you would need to fit a parameter-based model. What's the issue here? It seems as though we're done. We should just keep using the permutation-based model. The issue is precisely that this low variance property is true for the maximum likelihood estimator, which is the solution to a non-convex problem, and you can't actually compute it in polynomial time. So in order to take advantage of this low variance property, we're going to need something tractable that we can compute. Well, how do those do their way off on the right? The oldest estimators, due to Chatterjee in his celebrated matrix estimation via universal singular value thresholding paper, attain a rate with exponent 1/4. Note that the correct exponent is 1. And things have since been improved, but gotten bottlenecked at this exponent 1/2, the square root barrier, as it's called in the literature. And quite a few authors have conjectured that this red region is in fact hard. And as a basis for this conjecture, they've used the fact that the planted clique instance sits inside the permutation-based model. And if you've never seen this before, don't worry, I'll say a little bit more about this in the second portion of the talk. This doesn't have direct implications for this setting, unfortunately. And the second thing that they've used is the fact that this is precisely the rate of the spectral method for the problem. This is where the natural spectral method gets bottlenecked, and this is actually reflective of similar things that happen, for instance, in graph-on estimation problems, where we don't know how to beat spectral methods. So what I'll show you over the next few minutes is an estimator that is computable in polynomial time and surpasses the square root bottleneck. In particular, it attains a risk with exponent 3/4, and it does so in polynomial time. And over the course of describing this estimator, I'll also try and tell you a little bit about what went in to overcoming the hardness. Okay, so great, let's do that. So what do I have to do? I have to somehow convince you that this matrix in the permutation-based model can be estimated, and I have to give you an algorithm to do it. Well, what does a matrix in the permutation-based model look like? It has 3 unknowns. a row permutation pi1, a column permutation pi2, and an underlying bivariate isotonic matrix, which I'll call BISO, just for convenience. Now, what's a natural method by which you can estimate that matrix from noisy data? Well, first estimate the permutations by some method. And then once you've estimated the permutations, plug those in to an estimator of that bivariate isotonic matrix. In particular, treat those permutations as the truth and project your data onto that class of bivariate isotonic matrices. The second step is actually a quadratic program with linear constraints. And there are quite a few fast optimization solvers that will do it for you. What's perhaps nice about this, additionally, is that statistically, the risk will decompose into a measure of ranking error, how badly you got pi hat 1 and pi hat 2 wrong, and an error due to bivariate isotonic matrix estimation, the error made in estimating that matrix as though you knew the permutations in advance. So this decoupling is nice. And you can go in and show that the following inequality actually holds with high probability. The second term is of the parametric rate, little n over capital N, up to a logarithmic factor. And the ranking error is measured with respect to the underlying matrix M star. It asks if you view M star along its true permutations, pi star 1 and pi star 2, versus the estimated permutations, then how bad does that error get? And this is a very natural metric because if pi hat 1 happened to be an estimate of the permutation that flipped two identical rows of M star, then this error wouldn't change. Okay, so this is an oracle inequality, if you will, that decouples the two steps of the estimator. And what we prove is very simple. This ranking error can be controlled with a permutation estimate, which I'll describe in just a bit, with high probability at the exponent 3/4. So putting the pieces together, you basically get that star point that I promised before. Now, before I tell you about these permutation estimates, let me say a little bit about what that barrier really is and make yet another statistical connection for those of you who study these types of problems. Now, another metric in which this problem has been studied is called the row norm. This is an estimate of how badly the permutation does on any given row of the matrix. This is uniformly across all rows and it has various ranking applications. Now, it turns out that this Frobenius error, the ranking error that I talked about on the previous slide, can actually be bounded above via Holder's inequality by a row norm on the row permutation and the analogous column norm on the column permutation. And this is a method of analysis that actually pervades all the papers that I talked about a few slides ago. And what we show is that this potential function, although it's convenient and easy to work with, is somehow fundamentally bottlenecked. The minimax risk of estimation in the row norm, if you have the permutation-based model that you're estimating under, is lower bounded by the parametric rate to the power half. So you hit the square root bottleneck if you use this potential function, and it has nothing to do with computation. In particular, what that means is you're going to have to go after the Frobenius potential function directly. And this result is the consequence of making an actual connection between this problem and the problem of minimax testing. And this rate is the minimax radius of testing the positive authent against the zero vector. And I can say more about this in the end to anyone who's interested. So let's come back. This seems to, I've given you some intuition for the bottleneck itself. Let me tell you first, how does one go and get those permutations that I promised on the previous slide? And before we do that, let's actually consider the much simpler problem where only one of the permutations is unknown. So in particular, when I see my data, this is a salt and pepper plot of the noisy matrix, zeros and ones, I know in advance that the rows are already sorted, that the entries are sorted along the rows. All I have to do is estimate that permutation pi1 by everything I said before. But what's a natural way to do this? Well, look at every pair of rows. Look at your data on those rows. These are just zeros and ones. Based on that data, make a decision. One of these items beats the other item. If green beats yellow, add an edge in some underlying graph. Now, how might you choose that edge? How might you make this decision? A natural way that goes back all the way to Copeland in the 50s, actually Borda in the 1800s, is based on a very simple observation. A good item is one that beats a large fraction of other items. So the row sum is giving you quite a bit of information about whether to add that edge or not. In particular, a simple algorithm, when you see all the entries of this matrix, noisy entries, is to simply compare the sums of the green and yellow item. And if that difference is greater than a threshold, add that edge. How is this threshold chosen? It's chosen as to be the standard deviation of summing these n independent random variables. Now, the constant and the logarithmic factors there are for high probability bounds, and you can tune them if you want the probability bounds to change. So do this for every pair of items. And then once you have this graph, output a topological sort. That's any permutation that respects all the orderings on this graph. Now, this is a completely reasonable way to give you pi1. But it turns out that this method is actually not optimal. And the reason it's not optimal is because of this threshold. It's too high. Let me just sketch why. Imagine the two items that you were comparing actually had the following means. The means were identical except for a block of size square root n on the second item. Now, taking noisy row sums is going to completely destroy the signal. In particular, with constant probability, yellow is going to look better than green. But if I told you that these were, in fact, the underlying means in the first place, you'd be much cleverer. You would actually zoom in to the last square root n entries, thereby keeping the signal in the problem the same, but reducing the noise. And what you can do is prove a structural result about the monotone cone that suggests an algorithm from this intuition. Take your data and split it into blocks of size square root n. Instead of taking row sums over the entire row, now just sum over the blocks. If the sum of one item beats another one on any of the blocks by a threshold, add an edge. Now, crucially, that threshold is much, much smaller than before. It's square root of the block size, which is n to the 1/4. Now run the rest of the algorithm exactly the same way. Now there are lots of questions you might ask. For instance, why is square root n the right size? And it turns out that that's because it balances natural notions of estimation and approximation in this problem. And furthermore, this algorithm actually gives you row norm control in the case where you only have one permutation. This particular control is somehow fundamental and it validates the algorithm. It coincides with the minimax risk of testing the difference of monotone cones against 0. Now, for those of you who've been listening, it's clear here that I'm cheating. I've basically taken out one entire permutation and I told you all of this stuff. What happens when you have two unknown permutations? Well, I gave you an algorithm for when one of the permutations is known, so why don't we try and use it? In particular, take our data and estimate a column permutation by taking column sums, which are just as valid as the row sums. Cluster the columns if their column sums are close, form these blocks, and then apply the same algorithm from the first portion of this slide. Now, there are quite a few difficulties here. For instance, the blocks now are no longer of the same size because columns could cluster differently depending on how the underlying mean looks. And in order to handle all of this, you need some additional technical effort. In particular, you can no longer use the row norm as a potential function. You have to directly handle the Frobenius ranking error. But up to these technical issues, this is the algorithm that gets you that star point. For those of you who study random graphs, the first algorithm was based on degree-based sorting. And the second algorithm is a much more careful neighborhood-based algorithm, where the neighborhoods are defined now by the column sums. Okay, so I said a lot, and there are actually quite a few questions one could ask on top of this. For instance, why can't you recurse this idea? Why can't you do it again and again? There's still a statistical computational gap. It's not gone. I mean, the exponent is 3/4. All of these are completely valid questions, and I will address them at the end of the talk. So if you have those questions, please hold on. But if you have other questions, I'm happy to take one of them now. If Jihong, if you feel like there was something in the chat, or if you have one.
No, I think you can go ahead.
Awesome. This is being recorded and all that, so I hope they cut that out. But awesome. So what did we do in this portion of the talk? I basically considered the class of permutation-based models for pairwise comparisons. And I hope to have convinced you at the end of all that the interface between statistics and computation is extremely interesting when you consider worst-case risk properties of efficient estimators. Now I'm going to switch gears. I'm going to consider the same type of model for higher order comparisons. What if you don't just have two alternatives, but more than two alternatives? And now we'll see that the interface between statistics and computation manifests once more, but now when you study adaptation to structure in the problem. This is joint work with Richard Samworth at Cambridge. All right, so let's get right into it. What is a multi-way comparison? And I'll motivate it using the picture I showed you in the beginning of my talk. This is the depth map example where a crowd worker is shown a picture and is asked what point is closest to them. So the objective is to create a 3D depth map from feedback of this form. So notice that this is still a comparison now, just not between two items. There are three items. And in particular, what that means is that the stochastic model is no longer a matrix, it's a tensor, a third order tensor. Right? More generally, if you had D alternatives, then what you'd like to model is the probability with which the first alternative is chosen from those D alternatives. The probability that I1 is chosen from the tuple I1 through ID. So once again, this is just a probability model for your data, and a statistical model that's pervaded the literature for a very long time is based on the same weight-based assumption. Associate with each item a scalar weight, and now employ this multi-class logistic function to actually generate a probability. This goes by many names. It's a special case of what's called the Plackett-Luce or the multinomial logic model. And these have been extremely influential in the study of choice models in the past. But the frame that we've been operating in should already tell you that what we'll be interested in is a flexible generalization of these models, where if I put the best item on top of the tensor and the worst item on the bottom, then I have monotonicity relationships along each dimension. But because I don't know the rankings in advance, this defines a permutation-based model for multi-way comparison data. Now this has a name. In economics, it's called simple scalability. It goes back at least to the 60s. And it generalizes the weight-based model, much like you saw strong stochastic transitivity generalize the parameter-based model when D equals 2, the pairwise comparison setting. Now for the statisticians in this Zoom room, it should strike you as a little bit odd. We are now trying to think of a non-parametric model in higher and higher dimension. That's the number of choices getting larger and larger. And soon fitting these models is going to become quite prohibitive. So an interesting question here is there structure in these applications that we can use that is motivated, but still keeps the non-parametric nature of the model intact? In order to describe this, I'll actually use the two-dimensional example because it's very hard for me to do this in multiple dimensions and still make it work on a screen. But to motivate structure, just look at this example on your left, this picture of a depth map. If you were asked to label this example, you would probably think of all the points, items, on the bark of this tree as being at equivalent depths. And Kerry Mengerson actually alluded to this in her talk as well, a sort of interesting clustering that happens in item space or user space. And that's precisely what we're going to try and leverage, that items can often be clustered. And once these items are clustered, this defines structure in the underlying object of interest, the comparison probability matrix. Once you've made this partition, the entries on each block of the partition are piecewise constant. What is this saying? Operationally, you are indifferent between different items in the same cluster. And for that reason, this is called the indifference set assumption in the comparison literature. So notice that this piecewise constant structure doesn't exist in isolation. It is in addition to the non-parametric structure that already existed, the bivariate isotonicity. And furthermore, the latent permutations in the model will ensure that this piecewise constant structure is something you don't know in advance. As an assumption, this actually marries two assumptions in disparate fields, the literature on non-parametric statistics and shape constraints, as well as the literature on planted partition models and the stochastic block model, for instance. Okay, so now we've defined structure in the underlying problem to try and evade the curse of dimensionality, if you will. And the specific goal of this portion of the talk is going to be to try and understand if we can adapt to this structure. Can we leverage it without knowing of its existence in advance? We're going to ask fundamental questions of that. So let me formalize the adaptation question in this setting. Recall that we have indifference sets and give the sizes of these indifference sets names. Call them K1 through Ks. S is the number of indifference sets. And let's call I of K1 through Ks the permutation-based model. That's a d-order tensor which obeys this non-parametric shape constraint with unknown permutations, but also respects the indifference sets of these sizes. So this is a structured tensor in our model. And the question we want to ask is, can we exploit this structure with an algorithm without knowing of its existence in advance? So that's a foundational question, it would seem. So in order to understand it, let's actually consider the simplest possible observation model, where you take the tensor, in this case, the model is represented by T star, T for tensor, and you observe it in noise, where the noise is just IID Gaussian entry. Now, there are lots of questions you could ask me here about partial observations, Gaussians, and so on, and I can answer them later if you'd like. But for the purposes of this talk, let's just keep the model simple. Now, the number of samples that you see is basically the size of the tensor, little n to the power d, if I have d choices. That is, the tensor is in d dimension. How am I going to measure adaptation? Well, let me give you a very natural notion that goes back to lots of literature on non-parametric statistics. Recall our notion of the worst case risk over some model class. So again, here I'm going to take the squared L2 risk, just like before. I'm going to normalize by the size of the object, which is now capital N, and I'm going to take the worst case over all possible tensors in the class C. So that's going to be RC of t hat, just like before. Now, what's a nice operationalization of adaptation? I argue, well, not me, lots of people have argued that this ratio is actually a reasonable way to think about it. On the numerator is the worst case risk of t hat over the class of interest, I of K1 through Ks. And in the denominator is the smallest possible risk you can achieve over that class. So if this ratio is small for your estimator t hat, you have adapted to the structure in the problem because your risk is comparable to the smallest possible worst case risk. But we don't just want to adapt to one such structure. We want to be able to adapt to any such possible structure without knowing it in advance. And so you can actually take the maximum of this ratio over all possible such structured tensors, which is effectively a maximum over all possible allowable indifference set sizes. And this quantity is what I'll call the adaptation factor or the adaptivity index for the problem. So this actually goes back well into the 90s to Lepsky, his co-authors, and so on. And it's made some recent resurgences in the associated literature. Right, so this is going to be the object of interest now. And just to be technically correct, what I will consider for the rest of this talk is some high probability analog, which I'll not put on my slide just for brevity. And the question we'll ask is, what is the smallest adaptation factor achievable by a tractable procedure? Earlier, we were interested in the worst case risk. Now I'm changing the question to ask something about adaptation. Right, so we want t hat to be tractable as well. Okay, great. So now I've set it up. Let me just quickly tell you on one slide what our results are, and then I'll delve into one of them, maybe two of them, depending on time. So our results can again be sketched on a two-dimensional plot. On the x-axis now is the adaptation factor instead of being the worst case risk. And the notation is on the top right for anyone who's forgotten it. So note that the adaptation factor is trivially lower bounded by 1, just by definition, right? But what we show is that if you also want polynomial time adaptation, then that's lower bounded by a much, much larger quantity of the order n to the half times 1 minus 1 over d. And this is conditioned on something called the hypergraph planted clique conjecture, which I will introduce on the next slide. So operationally, what that means is efficient, computationally efficient adaptation in this problem, at least to this class of structures, is bottlenecked fundamentally. And this establishes a rigorous statistical computational gap on the adaptivity index. Now, even though there is a gap, you can still ask, well, is there a tractable estimator that does adapt? Even if this is the limit, does it achieve that limit? Well, the answer to that question is actually significantly subtle. What we show is that any meta method of the form that I introduced in the first portion of the talk, that is one that estimates permutations and then projects onto the isotonic cone that is consistent with those permutations, has a much, much larger adaptation factor for any dimension greater than 4. And this gap gets larger and larger as the dimension grows. So this now includes every algorithm that I talked about in the previous portion of my talk, or variants thereof, including our own. So something fundamentally different is going to be required if you want to be able to adapt to this structure. And finally, I'll show that there is in fact a well-chosen modification to that meta method that adapts with the optimal adaptation factor for polynomial time algorithms. And furthermore, and this I think is interesting but orthogonal, its computational complexity also adapts to underlying structure. Okay, so I've said a few things there, and if you are going to take something away from this portion of the talk, it should be this slide. But let me try and sort of tease apart two of these results just over the next few minutes, so that you get a flavor for what's really going on. So I'll focus a little bit on the computational hardness result because I think it's complementary to the sorts of things I've been saying so far. And then I'll come back and say a little bit about how you might design a polynomial time procedure and give you that star point. Okay, so in order to actually tell you about the computational hardness result, I have to tell you about the hypergraph planted clique conjecture. For those of you who've seen the planted clique conjecture, the one-line summary is that it's a higher order extension of it. But in more detail, it's actually a hypothesis testing conjecture on random d-regular hypergraphs on n vertices. These are random hypergraphs, and what you have to decide is between two hypotheses. The null is that the random hypergraph is Erdős-Rényi. Every possible hyperedge in the graph is generated independently with probability half. The alternative hypothesis is that there's a planted clique. A set of size k from the n vertices is chosen uniformly at random, and I've added a clique to that set. Every possible hyperedge has been added. Every other hyperedge outside that clique is again chosen with probability half independently. Now, the difficulty of this testing problem is captured precisely by the size of the planted clique. The smaller the clique, the harder it is to distinguish the hypotheses. And the hypergraph planted clique conjecture says that there's actually a threshold. If the clique is smaller than little o of square root n, then any test that runs in polynomial time in the size of your input, which is little n to the d, cannot succeed in distinguishing these hypotheses. Succeed here should be thought of as, type 1 plus type 2 error strictly less than 1 or something like that. But I won't get into the details for the purposes of brevity. Now, this is in spite of the fact that the information theoretic limits of the problem are significantly smaller. You can detect it if you're given full computation for a much smaller clique size. But the hypergraph planted clique conjecture says that that clique size is much, much larger. And quite a big line of work, quite recent now, has actually demonstrated that many polynomial time algorithms, many classes of such algorithms, including spectral methods, low degree methods, MCMC methods, actually get bottlenecked precisely at this point. And so there's quite a bit of evidence to support the validity of this conjecture. Okay, so this is the conjecture we're going to take for granted. Now let me try and tell you how this relates to adaptation in our problem. So I'll try and sketch the argument for you. I will not be precise in any sense of the word, but hopefully you get the main ideas. So the first step is to take this conjecture about hypergraphs, turn it into a conjecture about tensors. After all, we are interested in tensors in this portion of the talk. And you're able to do that via a technical reduction that maps the null hypothesis here about the Erdős-Rényi graph to a null hypothesis where you have a random tensor, which is a Gaussian tensor with zero mean. The alternative hypothesis with a planted clique in the graph corresponds to an alternative here, again, a random Gaussian tensor, but with a mean that has an elevated subtensor. So you should think of that as the planted model in tensor land. All right. So that's a reduction I won't spend very much time on. But now you actually have a hypothesis test on tensors. And now I have to try and convince you that once you actually have an algorithm for the permutation-based model that adapts to structure, such an algorithm can be used as a hypothesis tester here. Well, how might you do that? Well, notice that the underlying means of these two hypotheses, this is just a schematic, are what you want to tell apart. What makes it difficult is that there is noise, right? The actual Y that you see, somehow makes it difficult for you to tell these hypotheses apart. However, the underlying means, and you can convince yourself of this, both belong to the permutation-based model. And furthermore, they both have a small number of indifference sets. The null hypothesis has one indifference set, it's the all zero tensor, and the alternative hypothesis has two indifference sets. So an algorithm for the permutation-based model that adapts to structure is going to be able to effectively denoise my observations. And once these observations are denoised, I should be able to employ some very simple thresholding procedure to actually distinguish the hypothesis. Now, this was just an intuitive explanation. You can make all of this quantitative. If the underlying algorithm T hat actually has a small adaptivity index of the order on the previous slide, then you can show that the test will succeed when the planted clique has size little o of square root n. So putting together the pieces, if you believe the hypergraph planted clique conjecture, then such an estimator cannot be computable in polynomial time. All right, so that gives you the computational lower bound. So hopefully, at least intuitively, some of the things that I said are clear. So now I have to try and tell you how one might achieve this lower bound with an estimator. And note that the old meta method is just not going to work. I cannot estimate permutations and then project onto the isotonic cone. I have to regularize that method in some way. And what's a natural way to impart additional structure into a method of that form? It's to no longer estimate permutations, but estimate now partial orders up to noise. Let's not commit to a permutation or a ranking. Let's only commit to an equivalence class of rankings. And once we do that, let's actually modify the projection step. Let's now project onto matrices that respect the ordering given by the partial order, but are also piecewise constant on blocks of the partial order. So this additional averaging operation is hopefully going to add quite a bit of regularity to the problem. Now, this is only an additional linear constraint, so the computation doesn't change. In fact, you can show that the computational complexity improves, and I'll say a little bit about that. But statistically speaking, exactly as before, the risk will decompose, and you expect gains to happen on both of those terms. The ranking error will hopefully get averaged because you're taking this piecewise constant average. And the isotonic regression error will hopefully be much smaller now, because now you're projecting onto a class of functions that has much, much smaller complexity because it's piecewise constant over blocks. So this is a modification of that meta method. How do I give you a partial order? And that's basically all I'm going to do and conclude. Well, the natural thing is, again, go back to the exact same estimator we had before, which is giving you pairwise orderings between the various items in your problem. Earlier, we gave you a topological sort of this graph. That's a full permutation. Now we want to give you a partial order from this graph. How do you do this? You employ an algorithm that goes back to Mirsky in the 70s, which says you can take such a partial order and decompose it into disjoint antichains. An antichain is a collection of vertices where no partial order is actually specified between those vertices. So this is an example of an antichain for this graph. So now we no longer get a permutation, we get a partial order, just as we wanted. I still haven't told you how to add those edges. And in fact, you could add the edges exactly the same way that I said in the first portion of the talk. But what we show is that when D is greater than 3, this is actually overkill. Just the analogous row sum in this setting, with some bells and whistles that I will not actually describe now, attains the rate that I promised in that star point on the plot. And this Mirsky partition estimator actually has adaptation index that is bounded precisely by the quantity that we showed a lower bound of the order in the previous slide. Intuitively, this should make sense to you. When you see your data and you block your data, if lots of the random variables that you see all look similar, then it's probably likely that the underlying mean looks similar. So the averaging operation adds regularity that's completely reasonable, especially when you have indifferent sets. Now, what we've shown you really is a theorem that tells you that this is the optimal way to do it. But just intuitively, that's basically what you should take away. Now, from a computational perspective, and I said I'd touch upon this, both of these estimators, the Minsky partition estimator, as well as the estimators you saw in the previous part of the talk, have the same worst case complexity, n to the 3 halves. But if there happens to be an indifferent set in the problem of a small size, then the Minsky partition algorithm will run in linear time. In other words, the computational complexity of estimation under structure adapts to that structure. It doesn't know anything about it in advance, but it somehow adapts. And I think this is quite interesting as well. Okay, so I've said quite a few things, but hopefully at the end of all this, from both portions of the talk, what I hope you'll walk away with is that there is this class of permutation-based models. It's a very interesting combinatorial structure that's based on non-parametric assumptions that leads to many, many interesting computational as well as statistical problems. And considering the worst case risk like we did in the first portion of the talk, or adaptation like we did in the second, is very useful to understand the behavior of various methodologies at the intersection of statistics and computation. There are things I didn't tell you about. For instance, I only considered particular sample size regimes. It turns out that in other sample size regimes, you actually see lots of phase transitions in this problem. And it's quite interesting that we're actually minimax optimal in some of them. I didn't tell you about worst case risk in the multi-way setting, but you can do that. And for the non-parametric statisticians in the room, I didn't actually tell you about implications for the non-parametric problem without unknown permutations. And it turns out there are in fact implications. For open problems, well, one thing I said right at the end of the first portion of the talk is that I left the statistical gap open, the statistical computational gap. And I asked if there's some recursive update that will somehow narrow it further. Well, it turns out that about a month ago, Liu and Moitra have a very, very nice method that actually builds on top of what I presented with some additional well-chosen tools and further narrows the statistical computational gap. So from 3/4 in the exponent down to 5/6 in the exponent. It would be very interesting to see what more would be required to get all the way down. From a modeling perspective, these are non-parametric models, but they don't immediately accommodate covariates, which is additional information about your items that you might have in many applications. What about non-transitive structure? Is there a natural way to have a non-parametric model in that setting? And really the one question that I really want you to walk away with is this connection between computation and estimation, which we explored using the worst case risk in the first portion of the talk and adaptation factors in the second portion of the talk. But what happens maybe if you don't consider point estimates anymore and we only think about inference, which I think is an extremely interesting and challenging problem, not just in these settings, but even more broadly. So that concludes my talk. Thank you very, very much for your patience. I'd like to thank my wonderful co-authors, and these are the 2 papers on which this was based. You can find the second paper is actually going to come up on arXiv very, very soon, but you can find it in my thesis if you really want to get at it. And that's, thank you very much for your attention, and thanks to XKCD.
Great. Thank you, Ashwin. I learned a lot from your talk. Great talk. And so now let's open for questions. And a question from the audience. So maybe let me start from the first one. And can you comment on your order of computation? And so in terms of n, and I think your notation is and also the dimension you use the d, or I don't remember what the notation you use. Yeah.
That's a great question. So in the second portion of the talk, which is actually reflective of the first portion of the talk, so that's what's on the bottom right there. So the algorithm has worst case complexity that's sub-quadratic. So it's capital N, the size of your data, to the power 3/2. This is true both in the first portion of the talk and the second portion of the talk. And what I said in the end was that if the problem happens to be structured, right? If you happen to have indifferent sets and the number of indifferent sets is small, so this particular row here, then the Mirsky partition algorithm that I just described is linear time. So it runs in time linear in the input. So the computational complexity is O of n. I mean, all of this is hiding logarithmic factors, but those are not terrible or anything. Those are just one log or something like that.
Yeah, that's very nice. I think that it's really nice to see the order is linear in the sample size. Yeah. So the second question I have is, if you have covariates, how can you set up your framework in the regression setting?
Yeah, that's actually a very, very good question. It's something we've given a little bit of thought to, but it's you can come up with lots of solutions that are somehow hodgepodge. You can sort of have this assumption sitting on top of a natural covariate assumption in linear land. And those are natural ways to do it. Those sort of will add flexibility to just simple covariate based assumptions. But I think the short answer to your question is it's a very, very interesting question, and we still don't have a satisfactory answer to it. So it would be great if there was a very, very natural looking non-parametric model that gave you covariate information simply, but then didn't incur the risk of just doing non-parametrics on covariate. So if you did non-parametrics and you have a lot of covariates, then you're going to immediately hit the curse of dimensionality. So you don't want to pay for that, but you somehow want to be able to still use model with ordering constraints. So yeah, it's a very good question, and it would be great to have an answer to it.
Great, thank you. Any other question from the audience? Okay, it's no more questions. Thanks, Ashwin, again for a wonderful talk and very intriguing. I really learned a lot. And so unfortunately, we cannot give you a plaque today. So we'll give you you will have your plaque at the meeting next year, MS meeting next year. So
Thank you very much.
Yeah, so okay, so wonderful. Congratulations. So good night.
Thank you.
Thanks, everyone.